Hi, this is John Whitaker for the Probability Graduate Level class, and this is our 5th video lecture. And today we want to continue our work on discrete random variables, and we're going to look at the variance of a discrete random variable. We're going to look at examples, formulas involving the variance. We're also going to look at a couple of specific types of discrete random variables, and during this lecture we'll look at 2 of them, and there will be more to come with certain aspects of them emphasized. All right, so let's go ahead and get started. And first thing I want to start with is a definition, and that is the variance of a random variable. So given a random variable x, so any random variable, the variance of x is denoted by VAR of x and given by the variance of x is equal to the expected value of x minus the expected value of x to be squared. So it's an expected value of this quantity. And so this can be thought of, this function, this x minus the expected value of x to be squared, can be thought of as a function of x. And we know how to take the expected value of a function of x by a previous definition we had in our last video. In terms of the idea, the variance, so this is a comment, the variance of x, in some sense, measures the amount of spread in the variable value. Okay, I wanted to give a formula for the variance of x, and we'll do it even though it's true in discrete and continuous case. We hadn't mentioned about continuous random variables, so we're concentrating right now on discrete random variables, and as a fact, the variance of x, so if x is a discrete random variable, then the variance of x is equal to the expected value of x squared minus the expected value of x to b squared. So we want to prove this fact. It's a useful fact. It's quite often the method that we'll use to compute the variance. And so here it is a proof. So we'll let x be a discrete random variable. Then, as we know from definition, the variance of x is equal to the expected value of x minus the expected value of x. That's the quantity to be squared. That's equal to the expected value. So if I multiply this out, it would be x squared minus 2 times the expected value of x times x plus the expected value of x to be squared. That's what it would be. So it's the expected value of x. Now remember, x in this case is a discrete random variable. Okay. So that's equal to, because it's a discrete random variable, from our definition, it's the sum over the output values for x, okay, of, here I'll write down, x squared minus 2 times the expected value of x times x, and then plus the expected value of x to be squared, and all of that, let's put the brackets here, times f of x, which is the PMF of the random variable x, probability mass function. So that's by definition of the expected value of a function of x. So here we can multiply this out, so we get the sum over all the x values of x squared f of x minus 2 times the expected value of x times f of x plus the expected value of x to b squared times f of x. And then we can break this sum of several things into several sums. So the sum is over the x values of x squared times f of x minus the sum over the x values of 2 times the expected value of x times f of x plus the sum over the x values of the expected value of x to b squared times f of x. Okay. Now, here, using that definition of the expected value of g of x, the expected value of g of x is g of x, with the discrete random variable, the sum over all the x values of g of x times f of x. So this right here is nothing more, this first sum, is nothing more than the expected value of x squared minus. For this sum, one of the things I hadn't emphasized, maybe, the expected value of x is a number, okay, provided the expected value of x is fine, but it's a number. And so this is a constant. And so 2 times a constant, well, that's a constant. So the constant can be brought out to sum, and so we have 2 times the expected value of x times the sum x times f of x plus, again, the expected value of x squared, the expected value of x to b squared, is a constant, so I can bring it out of the sum. That's what I'm doing. Sum over the x values of f of x. All right. This is equal to, so we have the expected value of x squared minus 2 times the expected value of x, and then that sum over all x values. I didn't write that down before, so I'm looking right here. The sum over all x values of x f of x. Well, that part right there is nothing more than the expected value of x. And then I'm going to say something about that sum of the PMF over all x values too. But right here, making that substitution for the sum over all x values of x times f of x. That's the expected value of x. And then it says plus the expected value of x to b squared. And then has the sum of the probability mass function values. But we know as a fact that the sum of the probability mass values that over all x values, that's 1. So it just be times 1 here. So this ends up being the expected value of x squared minus, this is 2 times the expected value of x times the expected value of x, which is the expected value of x to b squared. And then this is plus 1 of the expected value of x to b squared. These are like terms. We combine them. We end up with the expected value of x squared minus the expected value of x to b squared. That's what we were trying to get. So that proves the variance formula. The next thing I want to do is an example. So let's go back to that card problem we looked at so often during our last lecture. So suppose a card is selected at random from a well-shuffled deck. Let x, I think what we had was a heart, x of a heart, let that be equal to -1. X of a black card, we said let that be equal to, I think, 3. And then x of a diamond, we said let that be equal to 2. And then maybe we're asked to find the variance of x, some sense of measure spread here for this random variable. So discrete random variable, that's where we have the formula for it this time. Okay. Well, the variance, I'll say by n. The variance of x is equal to the expected value of x squared minus the expected value of x to b squared. Well, the expected value of x to b squared, this is the expected value of a function of x, that's equal to the sum of x over all x values. But the x values here that can be taken on by the random variable, -1, 2, and 3, of g of x, where g of x in this case is x squared, times f of x. That's equal to, well, -1 to b squared times f of -1 plus 2 to b squared times f of 2 plus 3 to b squared times f of 3. All right, so this is equal to 1. And remember, f of -1 is the probability that x is equal to -1. That's the probability we've got a heart, that's 1/4. Plus, this is 4. F of 2 is the probability that x is equal to 2, or the probability we've got a black card. That's 1/2 or 2/4. And then plus 9. F of 3 is the chance x is equal to 3. That's the probability that we've got a diamond. That's 1/4. That's equal to 1/4 plus 8/4 plus 9/4, so that ends up being 18/4 is what we get for that. That's what I have. Let me check, make sure I didn't make a mistake. 1/4, 2 is black cards, 2/4, 9. That's what I see here. Okay, 18/4, that's what I got. Give me 1 second, I just don't want to make a mistake. It's easy for me to make a mistake. So -1, 4, 2, 4. Okay. And then, now, the expected value of x, I think we did this before, but let's do it again. It's the sum over all x values, f of x. That's going to be equal to, when x equals -1, it's -1 times f of -1 was equal to 1/4, plus, it's going to be 2 times f of 2. F of 2 is equal to 1/2, so that's 2/4. Plus, here it's going to be 3 times f of 3. What is f of 3? F of 3 is going to be 1/4 again. 1/4 there. And so we end up getting, here is 4, it's 3 fours, and 6 fours. So we have to square that. In our formula. So when I square that, here's what I get. So the variance of x in this problem is equal to the expected value of x squared minus expected value of x b squared. And that's equal to, the expected value of x squared is really 9/2 minus, well, let's make it 18/4 here. Minus, the expected value of x was 6/2, which was 6/4, which is 3/2 to be squared. So this ends up being 18/4 minus 9/4, and that ends up being 9/4. So that's what we ended up getting for the variance here. All right, so that's an example of computing the variance. The next thing I want to look at is, a definition. So a definition, and I want to talk about what's known as a Bernoulli experiment. So a Bernoulli experiment, let's start off this way. Yeah, Bernoulli experiment. Is an experiment in which there are only two outcomes. Namely, we call them success and failure. Where the probability of success is designated to be little p. So that's a Bernoulli experiment. We'll do an example a little later on. Associated to a Bernoulli experiment is a Bernoulli random variable. So, there's another definition. Suppose a Bernoulli experiment is performed. Okay. Then, define, or let, x of success equal to 1 and x of failure equal to 0. Then x is called a Bernoulli random variable. Well, the first thing we want to list in terms of fact for a Bernoulli random variable is what its PMF is. I think I should say something else. So, if the probability of a success equals to little p, then we say x is a Bernoulli random variable in this case. with parameter p. The little p. Okay. As a fact, let x be a renewed random variable with parameter p. Then the probability mass function of x is, well, it's f of x, and what it's equal to is p to the x times 1 minus p raised to the 1 minus x, where the only output values for x and value are 0 and 1. All right. This makes a lot of sense. You know, if x was 0, that means that big X would have been equal to 0. That means that we had gotten a favor. What's the chance of getting a favor? It's 1 minus p. So if x is 0, p to the 0 is 1. 1 minus p to the 1 minus 0 is just 1 minus p. 1 times 1 minus p is 1 minus p. So when x is 0, the PMF that we've written down here does seem to work. When x is 1, that's f of 1 would be the probability that x is equal to 1. That's the probability of success. That's p. So when x is 1, we have p to the first, that's just p. 1 minus p to 1 minus 1, that's 1 minus p to the 0, that's just 1. P times 1 is p. So yes, that's why that function is the PMF. Well, note the sum as x runs from 0 to 1 of f of x equals to the sum as x runs from 0 to 1 of p raised to the x times 1 minus p raised to the 1 minus x. And if you expand that, you just get, when x is 0, you get p to the 0 times 1 minus p plus, when x is 1, we get p to the first times 1 minus p to the 1 minus 1. And that's equal to 1 minus p plus p, which is just equal to 1. So the sum of the PMF over all possible output values does indeed equal 1. That's what should happen when you sum up the PMF values. So I just verified that that happens for the PMF of a Bernoulli. Okay, as a fact, if x is a new random variable, with parameter p, then the expected value of x, well, that's equal to p. Let's prove that. So as a proof, note, or we'll let x be Bernoulli with parameter p then the expected value of x, remember we defined what that was, I already used it during this lecture. The expected value of x for a discrete random variable is the sum over all output values, so in this case it's 0 to 1, of x times f of x. So this will be equal to 0 times f of 0 plus 1 times f of 1. Well, that's 0 times f of 0 is 1 minus p, plus 1 times f of 1, which is p. And so this is 0 plus p is just p. So that proves that the expected value of renewing is just this parameter. The last thing I want to do in terms of factual information about a renewed random variable is look at its variance. So as a fact, if x is a renewed random variable, with parameter p, then the variance of x is equal to p times 1 minus p. Let's prove this. So here again we've got xp Bernoulli. With parameter p. Okay. Now, the variance of x by formula is equal to the expected value of x squared minus the expected value of x to b squared. That's what we showed today. And so we need to calculate each one of these. But I know what the expected value of x is. It's p. So this last part is just b squared. Well, what about the first part? The expected value of x squared. That's equal to, will be the sum over all the x values, that's 0 and 1, of x squared times f of x. So that would be 0 times f of 0 plus 1 times f of 1, which is just p. So, the variance of x, which equals to the expected value of x squared minus the expected value of x to b squared, that's equal to p minus, well this is p squared. We just did that, and that's equal to p times, when I factor out p, 1 minus p, and that's what we said. All right, let's look at an example. So a card is selected at random from a well-shuffled deck. Let x of a heart be equal to 1 and x of a non-heart equal to 0. Then, this is an example of a Bernoulli random variable. Where we're thinking that success in our drawing would have been getting a heart. And the chance of getting a heart is 1/4. So, the PMF, that's the first thing, is f of x is equal to, what is p, so that's 1/4, raised to x, times 1 minus p, that's 3/4, raised to the 1 minus x, where x equals to 0 and 1. 2. The expected value of x, well, that's just p, so that's 1/4. And finally, thirdly, the variance of x, that's equal to p times 1 minus p, and that's equal to 1/4 times 3/4, which in this case is 3/16. So that's an example of a Bernoulli random variable. Well, we will conclude today by looking at another example of discrete random variable that is really based on the Bernoulli random variable. It's just an extension of it, if you will. I mean that, a generalization. And we'll talk about certain facts from it, as well as do one example, and that'll be all for today. Facts will take a little while to prove. So here's what we want to talk about. Definition. Suppose a Bernoulli experiment is performed in independent times. Okay? Let x count, let's say, one other thing, where the probability of success equals to p, in each trial. Each time it's done. Then we say let x count the number of successes obtained in the n trials. Then x is called, it's a discrete random variable, it's called a binomial random variable. The b could be lowercase, I don't know why. Anyway. With parameters n and p. Okay. Okay, so first of all, let's say it's a fact. We're going to let x be binomial with parameters n. Then the probability mass function, the PMF of x is Here it is. It's f of x, you see the n, choose x, p to the x, 1 minus p to the n minus x, where x could be equal to, what does x count? X counts the number of successes. You did the trial n times. Well, you might have done the trial n times and got no successes. You might have done the trial n times and got 1 success. 2 successes. All the way up to the maximum number of successes you could have in the n trials is n. No, that's what it is. Let's see if we can kind of get an understanding of why this is the p amount. Well, remember these trials are done n times and they're independent of each other. So you want to say we had something like x number of successes. We did it n times. Let me write down the n trials. 1, 2, 3, 4, 5. We go on n. Okay. And we've got, let's say, x number of successes. Maybe it's 3. You could have a success here, failure here. Let's put success, failure, success. Maybe this was a failure. And then let's say this was success and the rest are failures. So we got 3. So this will be f of 3 in this case. Okay. Well, that's the chance that this happened because they're independent trials. The chance that we get success here is p. Failure is 1 minus p. Here's success, p. 1 minus p. Here's success, p. And the rest of them are 1 minus p. So how many, we multiply these together, because we have the independence of the trials. And this would yield p to the 3, p to the x in my case, and 1 minus p to the n minus 3, n minus x. So that's what we have. This part of the p amount. The question may be, why do we have this n choose x part written out in front? Well, this is only one way to get 3 successes. You could have had your successes appear on any one of the 3 of the n trials. So what you have to do to figure out how many such categories there are where you have 3 successes, where do the successes fall, is that you say for the n trials we pick 3 or x of them for which they're going to be successes. How many ways can we have n choose x? How many ways can we put successes within these n trials? N choose 3, n choose 3 for this particular example, n choose x in general. That's my explanation of why this is the n trial. Well, one thing we need to do is, or can do, is to show that if we sum this up over all output values for x, that we get 1. So let's do that next. That's based on the fact, that proof's based on the fact that is the reason this random variable is defined the way it is. Okay. So here, let's recall, maybe your mathematical past, something called the binomial theorem. Here's what it says. It says if n is a natural number, then the sum, then x plus y to the n is equal to the sum as k runs from 0 to n of n choose k. I want to write this below. The sum as k runs from 0 to n of n choose k, x to the, I'll write down n minus k, y to the k. So that's the binomial theorem. Now, using the binomial theorem, we can note that the sum as x runs from 0 to n of f of x, where f of x is the PMF for a binomial random variable, that's equal to the sum as x runs from 0 to n of n choose x. Then it was p to the x 1 minus p to n minus x. And if you'll compare what's written right here to what's right here, they are identical, except that the index here is x, where the index here is k, if you switch these around. Okay? So the 1 minus p is like the x, the p is like the y, everything's the same. So what this is equal to by the binomial theorem is the first guy, x, which is what's raised to n minus x. So it's 1 minus p plus y in this case is p, and all of that raised to the n. But that's just, well, minus p plus p is just 0, so that's just 1 raised to the n, which is just 1. And so the sum of the PMF over all possible output values for the random variable x is equal to 1, which is what it should be equal to. Next thing we're going to do is look at the expected value. Before I move on, here's the PMF. If you'll notice, this is exactly the same PMF right here that what we had for Bernoulli, except with the Bernoulli, n was equal to 1. We only did the trial once. So a binomial, a Bernoulli is a binomial where the trial was only done one time. Now, as a fact, if x is a binomial random variable, with parameters n and p, then the expected value of x is n times p. Again, for Bernoulli it was just p, so that's when n is equal to 1 for what we're having as a fact for binomials, expected value. As the proof, let's look at that. A little bit more involved. Let's let x be a binomial random variable with parameters n and p. Then, the expected value of x, well, it's the sum over all output values, 0 to n, of x times f of x, which is equal to the sum over all x values, x running from 0 to n, of x times n choose x, of p to the x, 1 minus p to the n minus x. Next line on the right has to do with when x is 0, the first term of this sum is 0, because we have 0 times something. That's just 0. So might as well just run the sum from x running from 1 to n. That's what we're going to do. This is equal to the sum as x runs from 1 to n of x. And then n choose x is n factorial over n minus x factorial over x factorial. And then we have p to the x, 1 minus p to the n minus x. Okay, the x here and the x factorial, there's x times x minus 1, x minus 2 all the way down to 1. So the x that's involved in x factorial and this x will cancel. That's the sum of x from 1 to n. And let's just write that down as n factorial, and I'm going to write that as n times n minus 1 factorial over n minus x times factorial times x minus 1 factorial. There's p to the x 1 minus p to the n minus x. All I did, rewrite n factorial in this form, and say this x cancels with one of those x down there, just leave an x minus 1 factorial. This is equal to the sum as x runs from 1 to n. Let us pull out an n and a p. And then look at what remains. So this is n minus 1 factorial. And where I'm going to write this down here is n minus 1 minus x minus 1 factorial, and then x minus 1 factorial. I pulled out a p, it's p to the x minus 1, and then 1 minus p raised to the n minus x, which I'll rewrite as n minus 1 minus x minus 1. So the two minus 1s will cancel, we'll just have n minus x as the x minus. Exactly what we have. I can pull out a p because the index is x, and p is a constant with respect to that. And the same thing for n. N is a constant with respect to the index x. Right in that form. Because now we say this is equal to n times p. This is the sum as x runs from 1 to n. Here, this would be n minus 1. Choose x minus 1. That's what this big fraction is. And then p to the x minus 1, 1 minus p to the n minus 1, minus the quantity x minus 1. Now what I'm going to do is, np I'm going to write down as the same. What I'm going to do is express this sum using a different index. So I'm just going to let x, or I'll let j equal to, let's call it k. K equal to x minus 1. So I'm going to replace, that means then x will be equal to k plus 1. So this is equal to np, n times p is up. Now the sum that we had ran from x running from 1 to n. So k is going to run 1 less than that. So it was running from 1 to n, x was. So now k will run from 0 to n minus 1. Still got n minus 1. It used to be choose x minus 1. But now x minus 1 is the same as k. It was p to the x minus 1, that's p to k. And then 1 minus p to the n minus 1. And it was minus, it used to be x minus 1, but x minus 1 is the same thing as k. Now, if we look at this by the binomial theorem, this is np. But this part is, we're running up to n minus 1 instead of n, if you will. This is p to the k, 1 minus p, that's p to the index, the top of the summation here, which is also here, minus the index. That fits the binomial theorem perfectly, except what it would be is something raised to the n minus 1. But what the something is the 1 minus p, then plus p. And so this is n times p times 1 raised to n minus 1, which just equals to n times p. And that's the proof. Wonderful. Now, as a fact, we're now going to look at looking at a binomial and what's its parents. As a fact, if we let x be a binomial random variable, with parameters n and p, then the variance of x It's equal to n times p times 1 minus p. Okay. The p times 1 minus p was the variance of the Bernoulli. And then we multiply by n the number of trials that we do for binomial. But remember, a Bernoulli is nothing more than a binomial when the n is equal to 1 in the binomial. One trial. So yeah, that's kind of generalization. We're going to look at that fact. It's much like the expected value fact. Matter of fact, it's going to involve the expected value of a binomial. So here's the proof. We're going to let x be a binomial random variable. And, with parameters n and p. Then the variance of x by formula, we know it's the expected value of x squared minus the expected value of x to p squared. I already got this. This is the n times p, and I squared, so it's n squared, p squared. This is what I'm worried about. Well, the expected value of x squared is nothing more than the sum as x runs from 0 to n of x squared times f of x. That's by the definition of the expected value of a function of x. The g of x is what we call it generically. That's going to be equal to the sum as x runs from 0 to n of x squared times n choose x, p to the x, 1 minus p to the n minus x. Well, again, when x is 0, we just get 0 in the first term, so might as well start from x equal 1 to n of x squared. Here this will be n factorial, n minus x factorial over, this will be x factorial. Again, p to the x, 1 minus p to the n minus x. Now, one of the x's in the x squared, remember this is 0 here. One of the x's in the x squared cancels with one of the x's in the x factorial, the x in the x factorial. So we get a sum as n runs from, oh, it's not 0, it's 1. Oops, I made a mistake. Remember, we already said, let's just start from 1. 1, x, n factorial over n minus x factorial. This would be x minus 1 factorial. This would be p to the x, 1 minus p to the n minus x. Okay. Remember, we're trying to find the expected value of x squared. Not that much more to go on this proof, but we've got to do example 2. So, continuing on, what we're going to have is a sum. Let's pull out something. Let's pull out an n and a p. The sum as x goes from 1 to n of x. So when I pull out an n, it's from an n factorial. And so it's n minus 1 factorial. This would be over n minus x factorial. Here is x minus 1 factorial. We'd have p, it used to be the x, so now it's x minus 1, and then 1 minus p to the, here it was n minus x. All right. Now, this is n times p. Sum as x runs from 1 to n, x. Here, I'm going to rewrite this as this is the same thing as n minus 1. Choose x minus 1. This is similar to what we did for the expected value. p to the x minus 1, and then I'm going to rewrite this as 1 minus p, as is, raised to n minus x. I didn't rewrite it, just saying. Okay. Here I'm going to say, let's see, the n time, well, we're going to make a switch here in our index. So we're going to let, let's say, k equaling to x minus 1. So k plus 1 is what x is. So this is equal to n times p. The sum wouldn't run from 1 to n in terms of k. It would run from 0 to n minus 1. This would be, x is k plus 1. Here this would be n minus 1. Choose x minus 1. P to the x minus 1. X minus 1 is the same thing as k. And hey, this is k. Made a mistake again. And then 1 minus p. This would be n minus, well, x is the same thing as k minus 1. So I'll rewrite it as n minus 1 plus k. That's the same. Now I'm going to rewrite this as two sums, where really what I'm going to do is multiply k. I'm going to distribute this n minus 1 choose k, p to the k, 1 minus p to the n minus 1 plus k to the k plus 1. That's what I'm going to do. None major. This is equal to, okay, so it's n times p times the sum, and then it will be k times, let's take 1 from 0, raised to n minus 1. And then this is n minus 1, choose k, p to the k, 1 minus p raised to n minus 1 plus k, plus, well, I'm going to rewrite it as another sum. So this is the 1 part in the k plus 1. K runs from 0 to n minus 1. It would be n minus 1, choose k, p to the k, 1 minus p to the n minus 1 plus k. That's what it says. It's to the n minus 1 plus k. That's equal to, okay, this n, how do we understand this first? Let me get it myself. We understand this first sum as this looks like this part right here, the PMF of a binomial random variable with parameters p and n minus 1. And having the k out front of it, k is here, that's the expected value. So this sum is the expected value of binomial random variables with parameters n minus 1 and p. So the expected value of that is n minus 1 times p. Okay, that's this part. Plus, what this part is by the binomial theorem, is just 1. So this is equal to n p times n minus 1 times p plus np. Now, what was it that I just found? Well, that was the expected value of x squared. So, the variance of x, which is what I'm interested in, is the expected value of x squared minus the expected value of x to b squared. Okay. Well, look, it's this quantity right here, so it's equal to np times n minus 1 times p plus np minus the expected value of x we showed was np, so it's n squared p squared, which is equal to, okay, so here this is going to be n squared p squared minus, this is going to be np squared, okay, plus np minus n squared p squared. I'm going to finish it right here. So look, this minus n squared p squared and this plus n squared p squared, they cancel each other. So this is equal to, I'm just going to get it right. This is np minus np squared, which if you factor out np, this is 1 minus p. That's what we were trying to show. So the variance of a binomial is n times p times 1 minus p. That's what we're going to show. Let me do one example. We'll call it this. As a quick example. Okay. A card is selected from a deck. Its suit is noted, and the card is returned to the deck. And the deck is reshuffled. This is done 5 times. Let X count the number of parts. Obtained in the 5 trials. Okay? So we do this thing 5 times. How many hearts did we get? All right, that's an example. And so, as you can guess, X is binomial. So X is binomial with parameters n equal to 5 and p equal to 1/4. Chance of getting a heart, 1/4 of the stroke. PMF of X is f of X. So it's n choose X, that's 5 choose X. P, that's 1/4 to the X, and then 1 minus P, that's 3/4 to the 5 minus X. And again, X could be equal to 0, 1, 2, 3, 4, or 5. Second thing I want to talk about is the expected value of X, which is NP, and in this case is equal to 5 times 1/4, which is equal to 5/4. And that's the answer for the expected value. And third, the variance of X is equal to n times p times 1 minus p, which is equal to 5 times 1/4 times 3/4, which is 15 over 16. That's an example of a binomial random variable with its characteristics. Ladies and gentlemen, thank you very much for your time and patience. That's all for today.